B, suppose that the cost function is homothetic. That is, whatever restrictions you found to be necessary in A, they hold. And furthermore, suppose that gamma yy is 0. What's the degree of homogeneity of the cost function, of this cost function? The degree of homogeneity, as another hint, is connected to the notion of returns to scale. What's the working definition of returns to scale?
For example, double your output, or double your input, take your output, double for...
Or in this context, you don't have quantities of inputs. You have output and you have cost. Right? If there are increasing returns to scale, and you double your output, does your cost more than double, exactly double, or less than double? You know, or less than double. Okay? So the degree of homogeneity that we're interested in here is closely related. It's the same thing as asking, does this firm have constant increasing or decreasing returns to scale? What restrictions would be necessary to guarantee constant returns to scale? So this is a particular, you're going to end up, your answer to B is going to be symbolic. It's going to be stated in terms of the alphas and the gammas. And then, if there are constant returns to scale, what more do we have to say about our answer in B? Okay, so your answer to B is going to be stated in terms of the unknown alphas and gammas. And your answer to C is a little bit more specific. What exactly do we have to know about the alphas and the gammas to say that there are constant returns to scale? Differentiate the cost function with respect to each of the prices. That is fine, blah, blah. Use your resultant Shepard's lemma to derive the cost shares for each of the inputs. Well, you're already most of the way there because you did part A. In part A, you can look it up in your microtheory book. Another one of those things that you learned about in whatever it was you had with Bowman or whatever microtheory book. Shepard's lemma, by the way, is not just unique to economics. This happens to be that Shepard is the one who thought of the characterization. But it applies to other areas of endeavor where you're solving constrained optimization problems. Use the result Shepard's lemma to derive the cost shares for each of the inputs. That's, having done A, that question is going to be easy to walk in the park to do. Let's see. Using single equation OLS, estimate the unknown parameters of the 3 share equations for which you have data. That means that you're going to put on the left-hand side the share of labor, and on the right-hand side you're going to have the appropriate price and output terms that you need in the labor equation. So D tells you specifically what equations you're going to fit to the data in E.
What's the dependent?
Well, it will turn out that the dependent variable is like the share of labor, the share of capital, and the share of fuel, which are the 3 that you have. So everybody got it? In D, you're going to derive the 3 equations that you're going to, the coefficients of which you're going to estimate by OLS. And you're going to actually do that in E. Incidentally, do I think that the guys in Econ are going to remember this later on? Yeah. Do I think that the MSFE students are going to remember it later on? I don't think so. However, there is a method to my madness. Who's the guy who did the classical path-breaking work on the risk-return trade-off?
Sharp.
Sharp. Sharp's derivation of that representation was not a walk in the park. Yeah. Although nowadays anybody can go out and estimate the coefficients of a CAPM model. When you ask them, do they know where it came from? Not many of them can tell you, and very few, even fewer of them, could derive it. Okay, so this is to give you some practice in starting from a very structural orientation and deriving the things that can be used empirically, and used empirically in a very straightforward way. But it takes a lot of hard work to get to the point where you're implementing something that on the surface looks very simple and very compelling. What could be more compelling than the CAPM model? What a stroke of genius. And how much more simple could you get than the CAPM equations that you can look up in, I don't know, you look them up in Dun and Bradstreet? What are the S&P or wherever they are now? I don't remember anymore. But anybody can look them up. You can go out and collect data and you can estimate them until the cows come home and use them to design your portfolio. But a lot of hard work went into coming up with that very simple representation. F. Use the homogeneity restrictions to indirectly derive the estimates of the remaining parameters for M. So once you've estimated in E the 3 share equations, you go back to the homogeneity restrictions and you can solve for the coefficients you still don't know. Okay. So as I say, it's the first couple of steps that are pretty hard, and then after that, everything follows pretty quickly.
So what do you mean by the class between
What do I mean by what?
the class
You're going to get, without giving away too much, you're going to have, for example, a fuel equation that has a coefficient, an intercept, a slope times the price of capital. I don't know, it might even be the log of the price of capital. And you're going to have an equation for capital, which has, let's call this 0f, 1f, 0k, what? F, I don't know what that is.
I think that it's fuel.
I'm just giving a general example of what I mean by this cross equation or symmetry restrictions. Okay? So I'm just making up new symbols. So you have a first order condition for capital, which you turned into a share equation. So on the left you have K, and on the right you have delta F times the price of F. So this coefficient tells you something about the relationship between the price of capital and the amount of fuel that you bought. Look how nice and smooth these isoquants are. I ought to get the same picture whether I put L on the vertical axis or I put L on the horizontal axis. There's a certain symmetry in the picture. So there have to be some symmetry restriction. Okay. So the first subscript tells you what equation it came out of, and the second subscript tells you what variable it belonged to in that equation. So in the first line, the F tells me it came out of the F equation, and the K tells me it's the coefficient on PK. Here, it's the K equation, and it's the coefficient on PF. So the symmetry restriction is that for example, the elasticity of demand for capital with respect to the price of fuel ought to be the same as the elasticity of the demand for labor with respect to the price of the other, whichever one it was. Okay, so there's certain symmetry restrictions. It doesn't make any difference which variable you put on the vertical axis. You still get the same marginal rate of technical substitution, for example. Okay, so there are certain cross-equation restrictions. Those cross-equation restrictions implicitly are in the factor price frontier. Because you know that in putting together that Taylor series expansion, I have the second derivative of C with respect to F, and then with respect to K. I have the second derivative of C with respect to K, and then with respect to F. The symmetry restriction is I better get the same answer either way. So I made the argument before that these terms are second order terms in the Taylor series expansion. Implicitly, there's a gamma Lm times the log of PL times the log of PM, and there's also a gamma ML, which is the log of PM times the log of PL. But since the coefficient has to be the same, I just collapsed the restriction into the coefficient. Did you follow what I just said? Not exactly. Is that equality true or false? Has to be true, right? Must be true. So there has to be some symmetry in what we do. So from the three share equations that you derived in part, whichever one it was, D or E, one of the share equations estimates this, and another share equation estimates that. So you got to make sure that the coefficients, the corresponding coefficients in the two share equations are equal. That's called symmetry. So that's why I want to know whether or not your empirical results, because remember, when we estimate the three share equations, equation by equation, we're not imposing the symmetry restriction. We're going back but we're estimating the coefficients independently from one another. So after we've done that, we can go back and look and see whether or not we just got lucky and the symmetry was preserved. And if it turns out that the symmetry was preserved, was it just luck or was it something else going on in the mathematics? I made sure that even though the data that appeared in the two equations is slightly different, you still get the same symmetry preserved in it.